So our first example asks us to solve each equation. So in part A we have log base 6 of x plus 5 is equal to 2. And so what I'll do first is recognize that this is a logarithmic equation, and this is the example that we mentioned earlier. And so what I'm going to do is rewrite this as an exponential equation and try to solve it that way. So I can rewrite this as 6 to the exponent 2 is equal to x plus 5. And so from here it's pretty straightforward. 6 exponent 2 is 36, and that equals x plus 5. And then I can rearrange the equation from there to get 31 is equal to x. Okay, and if I check very quickly to see whether or not my answer makes sense, if I plug in 31 into the equation here, I get 31 plus 5, which is 36. And log base 6 of 36 would be equal to 2. 6 exponent 2 equals 36. Great. Let's take a look at the next one. First of all, notice that you have two logarithms, one on the left side, one on the right side. Only the one on the left-hand side has a variable in it. So I'm going to leave the right-hand side the way it is. I'm not going to rearrange it to move this over to the left-hand side or anything. And we'll talk about some examples where that may be necessary. But I only have one variable. It's already on the left-hand side. I'm going to leave it the way it is. Instead, what I'm going to do is rewrite the right-hand side using the power law. And so I'm going to take the coefficient of the logarithm and write it as the exponent on 27 instead. So I can rewrite this as log base 3 of 27 to the exponent 3. Okay, using the power law of logarithms. And so the property we talked about earlier, where you have the log of one expression equal to the log of another expression, as long as the bases are the same, then we know that the expressions must be equal to each other. So what that tells me is that the value of x is equal to 27 to the exponent 3. And we can figure out what that answer is by using a calculator. And so 27 to the exponent 3 gives me 19,683. So there's the value of x. And again, you can substitute in your equation and see whether or not it makes sense. Okay. Look at part C. We have log base 4 of x is equal to 2 log base 4 of 6 minus log base 4 of 3. And you'll notice that the left-hand side, the logarithm that you have is the only one with the variable in it. The right-hand side, the ones that you have do not have any variables. So I'm going to apply some of the laws of logarithms on the right-hand side to try to simplify it, and then use that property that we mentioned earlier, where if you have log base b of m equal to log base b of n, then that indicates that m and n must be equal to each other. So that's the property I'm going to try to use here. So let's use some of the laws of logarithms. So on the right-hand side, we're going to rewrite that. The left-hand side stays the way it is. So first I'm going to apply the power law of logarithms by putting the exponent of the coefficient of 2 as an exponent instead. So I get log base 4 of 6 squared minus log base 4 of 3. And because I'm subtracting two logarithms with the same base, I can apply the quotient law of logarithms, and I get log base 4 of x equals log base 4 of, now the quotient law indicates that if you're subtracting logarithms with the same base, then you can also rewrite it as division. So I can write 6 squared over 3, and so I end up getting log base 4 of x equals log base 4 of 6 squared is 36. 36 divided by 3 is 12, and so that tells me x is equal to 12. So using the property of logarithms that we mentioned earlier, I can ignore the logarithm and actually just look at the power part, and so I get x is equal to 12. Okay, let's take a look at the next example. This one's a little bit different. And so in this example, what you'll notice is that you have more than one logarithmic term that has a variable on it. So if you look at the left-hand side, you have two terms that have a variable term on it. So I'm going to use the laws of logarithms to try to combine them. And so on the left-hand side, what I'll use is the product law of logarithms. So since I'm adding two logarithms, I can use the product law. And on the right-hand side, I just have a number, so I'm going to leave it the way it is. And again, I'm going to use that property that we mentioned earlier, where if you have the log of one thing equal to the log of another thing, then you know that the two parts are equal to each other. And so let's start by applying the product law of logarithms. So I have log base 8 of x times x plus 2 equals log base 8 of 8. Okay, and so have a single logarithm on the left equal to a single logarithm on the right, and both the bases of the logarithms are the same, then that implies that this part here, the two expressions that I have as part of the logarithms, must be equal to each other. So, in other words, I have x times x plus 2 is equal to 8. And so now this is just a quadratic equation that I know how to solve, so I'm going to expand the left-hand side and bring the 8 over at the same time so that it's all equal to 0. And I get x squared plus 2x, and if I subtract 8 from both sides, I get minus 8 equals 0. And so I'm going to try to factor this since it is a quadratic equation, and I'll end up with two solutions. So if I factor this, I get x plus 4 and x minus 4 equals 0. And so that means, oops, x plus 4 and x minus 2. So product is negative 8, sum is positive 2, so that seems right. And so I have x is equal to negative 4 or x is equal to 2. And so I have two solutions here. But because I have more than one solution, I should check to see if either one of them may or may not be extraneous. Okay, so typically when you have more than one solution, there is a possibility that you have an extraneous root. So I'm going to check that first. And so I can check that very quickly by substituting it into the original equation that I have. And so if I plug in x equal to negative 4 in the first logarithm, you'll notice that I have log base 8 of negative 4. Now, whenever you're looking at a logarithm, the expression for the logarithm must be greater than 0. And so x equal to negative 4 will end up being a value that's less than 0. So that tells me that this is going to be extraneous. As soon as it doesn't satisfy one of the original logarithms, then automatically it's an extraneous root. Okay, even if I plug in x equal to negative 4 in the next logarithm, negative 4 plus 2 will give me negative 2. And again, it's not valid for this logarithm either. Okay, so I know this solution for sure will be extraneous. Okay, so I can ignore this solution. If I look at the next one, x equals 2, if I plug in 2 here, I'm looking at the logarithm of a positive value, so that's okay. If I plug in 2 here, I'm looking at the logarithm of a positive value again. So this one here is the solution that I actually want. Okay, so x equals negative 4 is extraneous, x equals 2 is valid.